Section 10.1, the chi-square distribution. In this chapter we'll be discussing a couple of new kinds of hypothesis tests which will require the use of a new probability distribution, and the distribution is called the chi-square distribution, and it's denoted chi, the Greek letter, with a square, and then some graphs are shown below. So just a quick comment about the chi. It's not chi, it's not chi, and it kind of looks like a fancy X, but best to look at the Microsoft version down here and kind of mimic that, but kind of a fancy X on one and then just a slash on the other. And then we're going to use this for some new types of tests that we're doing. So they're not going to be t-tests, and they're not going to be z-tests, they're going to be chi-squared tests. So let's look at these chi-squared curves. So you might notice chi-squares have df's to them like t's do. They're not necessarily bell-shaped. In fact, they look kind of right-skewed, and some of them severely right-skewed, like this one with a df of 4, and others just a little bit right-skewed, like this df of 16. So let's go ahead and note some of the properties that are on those graphs right here. The total area under a chi-squared curve is always equal to 1. We're going to be using these to find probability, so the total area always has to be 1, and that's why the ones that are shorter are also wider, so that the area still balances out. And chi-square curves are right-skewed, and one of the important things to note there is that they're not symmetric. Symmetric and skewed are somewhat opposites of each other, so once we state we have a right-skewed graph, then we know it's not symmetric at that point. And that means that tricks that we used before, like using the left side of a graph to help us figure out the right side, aren't going to work anymore. And then chi-squared curves start at 0, and they extend indefinitely to the right while the height of the curve approaches 0. So chi-squared curves have a starting point. They don't go to negative infinity and positive infinity on the two sides. They start at 0 and then they go forever to the right. And that actually is why we draw a vertical axis in when we draw these, not because we care about the height so much, but just to mark off where the two axes intersect is where 0 is, and all these curves are starting from there. And then as the degrees of freedom increase, the shape of a chi-squared curve begins to look more and more like a normal curve. So that's true, and you can see that happening a little bit as we go from df equals 4 to df equals 16. It becomes less skewed and starts to look more bell-shaped, but even at a df of 16, it still does look right-skewed and not bell-shaped. And in order for this to really start to look bell-shaped, the df has to get pretty large, larger than we'll probably see on the problems that we're doing. And just another quick comment about the curve starting at 0. That actually makes sense if you think of the fact that they're called a chi-squared curve. You should be surprised if something that's been squared has a negative value to it. And not that this is terribly important for what we're doing, but chi-squared curves actually come from squaring z-scores and adding them together. So if you randomly selected 8 values from a standard normal curve and got those z-scores and squared them all and added them together, you'd have one chi-squared value from a df equals 8. So the df actually corresponds to how many of those z-scores have been squared and added together. Alright, so the mean of a chi-squared curve, it turns out, is equal to its df. And if you combine that with the fact that the distribution is right-skewed, then we can say that the peak of the curve will occur slightly before the chi-squared value, corresponding to the number of degrees of freedom. And showing you that in a visual way, what that means is if you look at a chi-squared curve and it's got a df of 16, then if you were to drop down from the peak on that curve, the mean of 16 would be just a little bit to the right. When a curve is right-skewed, rather than the mean being at the peak, it's a little to the right. If the df is 8, drop down from that peak, and the mean of 8 is just a little to the right. If the df is 4, you can drop down from that peak, and then 4 would be just a little bit to the right of that. And the only reason that's important is because we're used to z-curves and t-curves that have a center at 0. If we know that you drop down from the peak and move a little bit over, that's your df. That gives us a little bit of a sense of the numbering on these graphs, and it'll help us place our test statistics later on. So let me go ahead and show you just a little bit about what we need to know with these chi-squared curves for moving into the next couple sections. Primarily what we need to know is how to find the area to the right of a specific value. It's going to turn out that all of our tests that we do in 10.2 and 10.3 are right-tailed tests. So if we know how to find the area to the right of a value, we'll be able to find p-values. So let's find the area to the right of chi-squared equals 18.22 if the df is 11, and they've also asked us to sketch that. So when I'm asked to sketch one of these, I start off by drawing both a vertical and a horizontal axis, and then I start at the intersection of those. I go up fast and down slow to make a right skewed shape, and I don't worry about how right skewed it looks. I basically draw the same shape regardless of the df, and then I drop down from the peak, and then I move just a little bit to the right, and that would be the df, which in this case is 11. So that just helps me know where to put this 18.22. This is 0, that's 11, so 18.22 would maybe be right around here. If this is a t-curve or a z-curve, I would expect that to be way out to the right, but if the peak is near 11, then 18.22 is not too far out in the tail. And then they want us to find the area to the right of that, so I'm going to shade that in. This is what I'm looking for. And I'm not going to use normal CDF to do it because it's not a z-curve, and I'm not going to use TCDF to do it because it's not a t-curve. So what I'm going to use to find that area is chi-squared CDF, and it works just like TCDF. You put in the left boundary, 1822, the right boundary, which there isn't one, so we'll use infinity, and then the degrees of freedom, which in this case is 11. And then we can go to the calculator and find out what that is. So when you go to the calculator, chi-squared CDF is where you should expect it to be. If you go into the distribution menu, just like you normally would, you have your normal CDF and you have your TCDF. And if you arrow down far enough, you'll find a chi-squared CDF. And then I can put that left boundary of 1822, the right boundary of infinity, and 11 degrees of freedom. And just kind of looking at the picture real quick before I press enter, there's a visible amount of area there, so I don't expect this to be one that comes out in scientific notation, but it's still kind of small, so it looks like maybe 5% or something like that. So let's press enter and see what we get. That seems about in the right ballpark. So 0.0766 is that area. And again, just looking at the picture, the total area under the curve is 1. I just have a small portion of that shaded, so for that area to come out around 0.0766 seems like a reasonable answer. Okay, so moving on to the second page, let's go ahead and look at another similar example. This time they're asking us to find the area to the left of chi-squared equals 3.055 with a degree of freedom of 6. So I'm going to start out by drawing a sketch. So I'll draw my vertical and horizontal axis. The chi-squared curve starts at 0, so I'll start out at the intersection. It's right skewed, so I want to go up quickly and down slowly. And then the df of 6 is also the mean, so if I drop down from the peak and just a little bit to the right, that'll be the 6. And then I want to place the number they asked about, 3.055, on my picture. This starting point is 0, this is 6, so 3.055 would be right about in the middle, so I'll do the best I can at hitting the middle there. So 3.055 is the boundary, so let me draw that up till it hits the curve. And this time they want the area to the left side of that, so I would shade this area to the left right here. And then I'm just going to find that using the chi-squared CDF, just like we did on the last one. So for chi-squared CDF, you want to enter the left-hand boundary, which we need to remember this curve starts at 0. So that's where that shading stops. And then the right-hand boundary would be 3.055. and the degrees of freedom, which is 6. So the main difference here between z-scores and t-curves when you're starting to do area to the left is your left-hand boundary is not negative infinity, but it's 0, because on the chi-squared curve, that's where the curve starts. And then we'll just go to the calculator, see what that works out to be. So we go into the distribution menu. We want to go all the way down to chi-squared CDF, left boundary of 0, right boundary is 3.055, and degrees of freedom is 6. And before I press enter, just taking a quick look at the graph and thinking about what the size of that answer might be, we've shaded less than half of the picture, and a lot of it remains unshaded, so I'd say this area is smaller than 50% for sure, but it's substantial. It's a lot of the curve that is shaded, so maybe it's 20%, 30% of the area, something like that. So let's press enter and see what we get. And it comes up to be kind of close to that 20% guess that I had. So 0.1981. It's always good to take a guess at it before you press enter, just to make sure that you're getting an answer that seems reasonable. Alright, so let's go ahead and summarize that real quick, this new piece of the technology. The chi-squared CDF, which we're using for these problems, is found in the distribution menu, and you may need to arrow down to find it. So for me it was just off of my first screen. I had to arrow down past that to number 8. And the structure of the command is chi-squared CDF, lower endpoint, upper endpoint, and then just like for the t-curve, you have to put your df, or degrees of freedom. Alright, that wraps up section 10.1.